This is Geotrig Lesson 3, Day 2 of notes. And so we're just going to keep on going here with the Pythagorean Theorem and Inequalities. And so this is kind of cool about this, is that obviously not all triangles are right triangles. Right triangles are pretty special. They happen to have a what? 90-degree angle, as the first blank says. So 90-degree angle. There are also blank triangles, angle bigger than blank, and blank triangles or angles are blank than 90. The first one is obtuse. Obtuse, because it's bigger than 90. That's a bad 9. And acute fuzzy ones. And those are less or smaller than 90 degrees. All of the angles, right? Now here's the thing, an obtuse triangle. So you mean all of them are bigger than 90? Can you have a triangle if all of the angles are bigger than 90?
No, because then it's like line.
Right, because what defines a triangle? How many sides? 3 sides, and all the angles add up to 180. If I had something other, okay, 90 is the biggest angle you can have, because a 90 plus a 90 is already 180. I can't put a third angle in there. So, obtuse triangle. What does it look like? Maybe that's what that blank's for.
What were you thinking?
It's been a while since I made these guys. And actually, this one might have been copied from another teacher.
Plagiarism.
It is. Yes, it's working together, collaboration.
We can do that on it.
So, what's an obtuse triangle look like in general? Something like that, yes? Where one angle, guys, is bigger than 90. And then the acute fuzzy ones, we kind of look at this one as kind of the universal acute one because it's, what kind, really? It looks really close to an equilateral, which all the sides would be the same, and the angles. But there's multiple versions of all of these, right? Ranging from, on the obtuse side, a bigger angle of 90 point something, all the way up to 178-ish around there. Because each end can be 1 degree. You can even be smaller than that. It'd be a really weird looking triangle. But is everybody okay with that? I think we all know that. So, next. It's a little smaller on the screen. That's why we print them off. But that's why those blanks are there. Let's go back. Now, the cool thing about it is we can put sides on here, yes? If I call these A, B, and C. C, guys, should always be what? The longest side. And Pythagorean's theorem says this, right? We just had it in the last slide. A squared plus B squared equals C squared. That should be true. Yes? Now, if we happen to have some side lengths given to us, what we'll find is that if it's an obtuse triangle, they won't be equal. A squared plus B squared will not equal C squared. If it's acute, it will not be as well. And so, this only works for right triangles. So I'm going to box that off. It's different when they're obtuse. When they're obtuse, I'm going to change the colors so we don't get it mixed up here, is A squared plus B squared. There's still a C squared, but one of these will be bigger than the other. If it's obtuse, look at your picture there. C is really big, right? And when you have something that's really big and you square it, it gets bigger. So therefore, if you'd used Pythagorean's theorem, and you notice that a squared plus b squared is less than c squared, that means the sides don't have enough length to include c in it. Is that you kind of get this idea? It almost looks like you're doing this. So c will be really big, but then this side won't be enough. There won't be enough swing room. When I go to swing that third side, I can't get to the hypotenuse at the end. So when it's an acute angle, a triangle, you still have a squared plus b squared, and you still have c squared. But when it's an acute triangle, it almost seems like, to use this Pythagorean identity or theorem, would almost seem like the sides are too long. So now you have something that looks like this, where your third side, sorry, wrong. I'm thinking this side is longer than, the two sides will be longer than what it needs to be. Okay? So we're going to show that in the next slide, where you're going to be able to tell me if it's an acute, right, or obtuse triangle. Any questions? And all it is are the sides bigger than the hypotenuse when squared, or is the hypotenuse bigger? So, 10, 9, and 3. The question is, could I build a right triangle with this?
No.
Or, if I built a triangle with those 10, 9, and 3 sides respectively, will it be an acute or an obtuse triangle?
Obtuse.
Well, here's the thing. You need to identify A, B, and C. C has to be 10 because it's the biggest one. So, maybe, guys, you need to say what C is. Does it matter what A and B are, though?
No.
So, I mean, if I really wanted to, I could still list them. A equals 9, because it's the first one, and B is 3. So this is what I like to do. I like to start off with 9 squared plus 3 squared. I'm going to use parentheses. And then I go over here and put 10 squared, which is C, right? And then maybe even put a box in the middle, because that is where my inequality goes, right? So the question is, which one's bigger? And then when we know that, we can be able to tell if it's obtuse, acute, or right. If it's equal, it's right. 9 squared? 81 plus 9 equals 100. No, it doesn't equal 100. It's less than, because 81 plus 9 is 90, and 90 compared to 100, it's less than. And so that means the C value is bigger. That's obtuse. And it kind of just seemed that way just by looking at the numbers, right? Are we seeing what we have to do?
Yes. Yes.
Then I want you to do the same thing with number 2. So we're going to use this pattern. What's A?
7.
7. What are we going to call B then?
9.
9. And so C then
Has to be 11.
has to be 11 either way, no matter what you do. So let's do this. Plain substitution or plain coach here. We are going to put in with parentheses. Guys, always use parentheses just in case you're trying to work with negative numbers. But you should know you'll never have a negative number working with triangles. Why? Because you can't have a side length that's negative, yes?
Yes.
And so this is 7, 9, 11. 7 squared. 49 plus 81.
And then 121.
121.
It's 131 and then 130.
Oh, 130. Okay.
Yeah.
And so, what side's bigger? The legs or the hypotenuse?
Acute.
The legs are, so this is an acute fuzzy one. So similar polygons. A blank is a simple, closed, coplanar on the same plane. Geometric figures whose sides are straight lines. It's all over this page. What is it? Polygon. So it's a polygon. So, what's an example of a non-polygon? A circle. A circle is a non-polygon. Now, it matters, I guess, yeah, we're just going to say it's not a polygon because by this definition, it has to have what? No, straight lines. So therefore, circle is not a straight line, so therefore, not a polygon.
No way I could have cheated on that either, so that's straight out of the thinker.
That is not a polygon. That is not a polygon. They're straight lines. Okay, guys, we're assuming those are straight lines, but it's not it's not simple. It's made up of polygons. This is also not a polygon. It's not closed. Okay, so we're kind of getting the idea there. So, what? Yes, this is definitely kindergarten stuff. We're just putting names to it. Okay. What's the most simplistic polygon you can have?
The
Triangle. Yeah, a pentagon would not be the most simplistic one. But a triangle would definitely be probably the most simplistic, moving up to a square/rectangle. Then we can go to a
doghouse.
Pentagon.
What?
Hexagon. Next would be a... No, we already had a hexagon.
Octagon.
No, that's a 10, right? Or 100. So, no, you're skipping. That's 6. Then we got to go to 7. Heptagon. Okay. Guys are getting a little rowdy. Okay. So we got there's more, guys. It goes on forever. You could have up to about 10, they start naming it as a decagon. But once you get past 10 and you get to 11, they end up just calling this a 11gon. Yeah, they say just kind of give up. We're not going to keep naming these things. So that's 11gon if they have 11 sides. Now, I think maybe we're going to name some of these on the next slide or two. But what's a vertice then? Vertice is a fancy way of saying a corner. Guys, I'm going to change the colors here. I'll make them purple, but that's a vertice, 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 and a vertice. Those are vertices. What is a side? How about connects vertices or corners? So our sides obviously are the things that are connecting them, and they will be
equal.
No, straight. Okay, they're going to be straight lines in these things.
There's an exclamation point. That must be important.
Very important, guys. It's nice to know this. Number of vertices is the same as the number of sides. You guys, they always will match up with each other. So know that. And notice, guys, that, well, in these problems, I guess they don't necessarily open up to a side. Triangles, though, if you notice, you can have vertices over here. Vertices, when we start to compare similar triangles and things, you'll notice that vertices will correspond with a side. But when we start getting larger polygons, you can't do that. Okay? This is why we print them out. Guys, this is on one of our pages. Please stop talking. Now, like I said, you have all these different shapes. We have something we are going to call, and I'm at least write this down if you don't have this, a regular polygon, and we have something called irregular polygon. The regular polygon, guys. regular polygons have all equal angle measures and have equal lengths. When I think of a regular polygon is what we call our ideal polygons. A square, an equilateral triangle, a stop sign, right? You see a stop sign, that's a regular polygon because all of the angles in it are the same, all of the side lengths are the same. That's what kind of makes it kind of aesthetically pleasing, right? And so take a look at all of these pictures here. This is a regular pentagon. All of the sides and angles are the same, but this is also a pentagon. So if you're not regular, then it means you are abnormal, irregular polygon, which is all the rest of them. Okay? Yes, look, it's possible to make a 7-sided regular heptagon. 7 sides. It does look funny, but it's possible. Most likely, anything that we ever make are going to be not so nice. That's an irregular heptagon. Now, as I was saying, we start to name them at 3 sides because that's a triangle. We go to a quadrilateral. We don't call them squares or rectangles. They're quadrilaterals. There's a whole class of them, remember, because a rectangle it's got parallel sides. It doesn't have to have those. Okay? Think of a trapezoid. It's a quadrilateral. It's 4-sided. So therefore, it still is a polygon. Then we go to pentagon. We call it hexagon, heptagon, octagon, nonagon. Oh, we do have. Oh, sorry, I was wrong. We do go up to 12. A dodecagon, 12-sided. Guys, for the most part, after 8. Most of us probably don't remember because we generally don't use it. But 10, decagon, deca for 10, sounds about right. So be mindful that there are names for these. And so in your problems in your book, it might say find the surface area of a dodecagon, which means it has how many different angles? Okay, decagon is 10. It means it also has 10 sides. And so way on the bottom, instead of having to write all this out, I left it on here. It's saying that you have consecutive vertices. Consecutive vertices, guys, is just when you start at one vertice and you go to the next one. It doesn't mean I jump from all the way from the top to the bottom here. I missed a vertice. Those are not consecutive. But when I'm going around, when I go and step on each one of those vertices, now the ones that are next to each other are called consecutive. Consecutive sides are the sides that are next to each other. Makes sense. And then the last thing, way on the bottom here, is called a diagonal. I'm going to go back up to this first pentagon. A diagonal, guys, connects a vertice. I'll change to red so you can see it. Connects a vertice to any non-consecutive. Non-consecutive. So, if you take a look at this, that one vertice way up top here has 2 diagonals. But wait a minute. Wait. Can't I say that this vertice here has 1, 2 as well?
Good.
But then, wait. This one has 2 as well. One of them is already taken up with one we talked about already. And then all of a sudden I get to this one down here and I realize that that one's already being taken up by 2 from the other one, right? Or from 2 others. How many diagonals are there in this pentagon? How many lines do you see? 1, 2, 3, 4, 5. Any others? No. Move on to the 7-sided one. 1, 2, 3, 4. Yes?
Yes.
Then we change colors, because we can. How about 1, 2, 3? Because the first one's already connected here, right? So we got 3, then we went to 4. Now all of a sudden I'll change to yellow and go 1, 2. And then I think there's one left. Oh, we use a nice brown color. Hey, did I miss one here? Uh-oh. Uh-oh. Where else did I miss? Oh, the yellow. The yellow? Interesting. And am I done? So, there's got to be a better way than me giving you a 50-sided polygon and tell me how many diagonals there are.
50.
There's more than 50. Take a look at this. There's like 15 of them there. So there's got to be a better way. So let's explore that in a little bit, not this slide. So diagonals, guys, there's many, many, many diagonals. Page 34, 1, 18, 19, 23, and 27. Have a fantastic day.